This second video in the series on Unity's Graph Toolkit version 0.4 will focus on setting up the editor features including finding cycles in the graph. The graph class and node classes handle all the features visible in the editor graph window. The first class I'll look at is the LayeredNMGraph, which inherits from graph. This is using the editor namespace, so it can only be called inside the editor and not at runtime. The first bit of code is all boilerplate. Setting the extension that will be used for the graph file, serializing the file, the default graph name, the actual value of the extension. ErrorMessage is not boilerplate. It is a custom class which just holds a little bit of data. Whether or not there is an error, what all the messages are, and then all the messages are concatenated so that they can be used easily inside a custom inspector. The error message is used to pass information out of the layered noise map and into other classes. In this case, for instance, there's an error here, and this message is passed out so that the scriptable object layered noise map can display it. Then we have creating the menu item. You can create an item from the menu, and that's just Asset, Create, Graph Toolkit, Layered Noise Map. We'll create Layered Noise Map graph. Next, creating the graph itself. The main function that will be called is the OnGraphChanged method. So whenever the graph is changed, this will be called. It is used for displaying errors. So a graph logger, which is similar to the debug logger, is passed in. It will show the errors in the editor graph window. Call the base class, and then call a custom class to check for graph errors. The custom class is also fairly straightforward and receives the graph logger. Creates a new error message, generates the ResultMapNodeErrors, and the CycleErrors. The ResultMapNodeErrors are fairly straightforward. You collect all the result map nodes, check the size of the array. If it's 0, set the error message to true. Put the message in the error message and send the error message to the graph window. The context will be this, the graph. Currently that has no effect, so this doesn't appear in the editor window, only in the console. Case 1 is no error when we have only one result map node. Again, when you have more than one, set the error to true. Set a single message telling you that there are many errors. And then for each of the errors in the graph logger, log a message for each one with the result map node as the context. This will produce a little red mark beside each of the result map nodes. The cycle check is the meat of this class. These variables are outside the method because the method is going to be called recursively. There's the visited nodes, the nodes in the call stack, recursive checked nodes, and cycle nodes, which is all the nodes were found to be in a cycle. So CycleNodes is emptied when we start this CycleErrors method. Then we call FindCycles, which will fill CycleNodes with all the nodes that were found to be in a cycle. For each node in there, we do something similar to what we did in ResultMapNodeErrors. Mark this as an error. Add the message to the error message. Log an error for each one with the node. So all the nodes will show with a little red mark beside them. The actual cycle check algorithm I got from Geeks for Geeks. The link here gives you a description of this algorithm and other algorithms for cycle checking. That will also be in the description. The FindCycles method. It's going to go through each node, so in this case there will be 4 as in the diagram on the side. And the reason for that is that the cycle util may only find one cycle node. And so to find them all, for sure we have to start at each node. The actual algorithm, the recursive part, receives the start node, checks if recursive check nodes has the start node in it. No, because it's empty. And the same with visited nodes. So we fall through to here and add the start node to both. So now visited nodes and recursive check nodes will have the 0 node in them. The next part is not part of the Geeks for Geeks algorithm, but it is to take into account that a graph from Unity GraphToolkit can have multiple edges between 2 nodes in the same direction. We can go from 0 to 1 in the direction 0 to 1 multiple times because we could be sending multiple pieces of data. In a normal digraph, that is not allowed. You can only have one edge in each direction. So it's one edge down and one edge up, or one edge in only one direction. So this is used to handle the case of multiple edges pointing in the same direction. We get the outports. We get the connection, which has a node. We check if we've already gone to that node from the current node. So if we've already gone from 0 to 1, we don't want to do it again. And we just continue. Then we have to add it in here, so we'll find it next time. Once we go from 0 to 1, we recursively do the check on node 1. So go to the next step. We repeat the procedure. We check for 1 in recursively checked nodes and visited nodes. They're not found, so we add them. And now we go down to 3. And the call stack keeps getting deeper. We check for 3 in visited nodes and recursive check nodes. It is not found, so we add 3 to visited nodes and recursive check nodes. But 3 has no outports. We get to here and this just falls through and says remove. So we are going to remove 3 here. And then we're going to return false, which means we pop the stack. So that's this one. We've removed 3 and we've popped the stack back up to 1. So we go back here. 3 gets removed from the call stack and from the recursive check nodes. We're back up here. We go down to 2. 2 is nothing unusual. We check for 2 up here and in the hash sets. We go down here. We add 2 in. Now we check for 3. We go to 3, and this time we check up here. In visited nodes, we actually find 3. So when we found 3, we didn't find it in the recursive nodes, but we found it in the visited nodes. So we popped the stack again, returning false again. We go from 2 to 0. This puts us at 0. This time when we check for 0, we find it in recursive checked nodes. We find it here at the very first, which means we're going to pop, but we're going to add it to cycle nodes, and we return true. We're here at isCycleCheck, and it's true, so we immediately pop again, returning true. This is the only line of code that makes a recursive call, so we'll keep returning true until finally we return from the original isCycleCheck call in FindCycles. If there is another node to process, we will clear visited nodes and recursive checked nodes, then call isCycle on the new node. When we complete FindCycles, we will log the messages for each node in CycleNodes. CycleErrors is the last line in CheckGraphErrors, and we are finished with OnGraphChanged. Sorry, I just dropped the marketing graphics on the video. While I sort them out, if you are enjoying this content, please leave a like. If you would like to see more videos like this, please subscribe. If you have any questions, suggestions, or spot a mistake, please leave a comment. Or join the Discord. The link is in the description, and comment there. If you need some Unity programming for an indie project, contact me at the link in the description. 10% discount on programming services if you mention this YouTube channel. The next thing to do is to look at LayeredNMNode, the abstract parent for all editor time nodes. We are still using the Graph Toolkit editor namespace. So this is an editor-only class that inherits from Node, and it has one abstract method I have added, which is new runtime node. This is used to return the runtime node associated with the editor node. It is not a requirement of Graph Toolkit, but just for this graph, that there is a one-to-one correspondence between the editor nodes and the runtime nodes. The first one I'll look at is the StandardGeneratorNode. It has the boilerplate for my nodes, which is to override the new runtime node method, returning the corresponding runtime node. In this case, StandardGeneratorRuntimeNode. Now over here, just to remind you what's in a node, it's got a name, it's a type, this is an option, and then it has 4 input ports and 1 output port. So the option is here, and its name is type, and in this case it's an enum. This enum comes from a height map generator class, which is used at runtime. It is a list of noise types and constant types. So we add a type of that enum, and then it has a default value. I've made it purlin. We have delayed and build. I will delay discussing delayed until I get to the SumNode, because it's easier to show what it does there. So then we override the onDefined ports, pass in an iPort definition context, and then we operate on that object calling its methods. So we add an import, it's got a type float, and it's got an identifier. So these all have to be unique inside one node. The identifiers are going to be needed in the runtime and the editor. So I placed them in the LayeredNMRuntimeNode class. They're just constant strings with literal values. And then we have a display name, a default value, and then we build it. Just to show you how these work, this had all those enum values. They have display names, and then this also will have a display name. So these other input ports are pretty much the same. There are only floats and ints used in this class. This is slightly different for the output port, and that's that you call add output port and it doesn't have a default value. SumNode is probably the most complicated node. It's still pretty simple. So it also defines an option, and it's of type int this time. Now the delays effect can be seen. When I change this to, say, 12, nothing changes until I hit enter. And then it expands the node to 12 input ports. So the delayed caused this not to be read immediately, but read after you hit enter. And then this is on defined ports. It gets the value from this option by name using the identifier dynamic port count. I clamp it at 20 because I didn't want the node getting too big in the graph editor. And then it just loops over, adding input ports with I at the end of the identifier and of the display name. And the default port is just an empty minimal two-dimensional float. And then the output map is the same as the previous node. RaiseNode is pretty simple. Boilerplate code followed by an input port map. And a float value for raise, and then an output port map. IslandNode is even simpler. It doesn't have any extra inputs, just an input and an output map. ShiftYNode is another simple one with the same ports as RaiseNode. And then finally the ResultMapNode is the simplest one because it only has an input and no output port. It will be writing its value directly in the LayeredNMGraph asset. One thing to note is that these Blackboard variable types, float, float array, and integer, are automatically created by Graph Toolkit. It reads the port types of all nodes and creates matching Blackboard types. Note, it shows all arrays as being one-dimensional arrays, even if the port was a two-dimensional array. The memory mapping of them is the same as multi-dimensional arrays, so it is not a problem. And that covers everything for this video. The next video will be on the runtime nodes and topological digraph sorting. Then later videos will cover executing the graph at runtime and the ancillary code for the scriptable object and mono behavior.